Okay, so here you can see the title of our paper, Numerical Simulation of Fatigue Crack Growth in Aircraft Structures with a Honeycomb Mesh. Now, this is actually a work in progress, which we had started recently, and some of these models are being developed as I'm presenting actually. So now I will show you the results so far and the future work that we plan on to continue with this. So fatigue behavior of materials is not so well known even today, and this is particularly true for composite materials, which are commonly used for aerospace structures, among other things. And here we decided to try to determine the fatigue behavior of aerospace engineering structural elements with a characteristic honeycomb mesh and made of some newer composites, because this is something that up to our knowledge, nobody has still worked on. However, to get there, we decided to first start with some simpler models using aluminum alloys, which are also a common material with far better known fatigue properties in aerospace engineering. So first, some simpler static models of the honeycomb mesh elements were made based on some of the experimental results so that we could determine the stress distribution under static loading, so to know where we can expect the fatigue crack to initiate. So the material we plan to use in the future is Nomex 410 paper and orthotropic composite. But before we can get to that point, we first need to verify that our initial approaches are correct by using simpler models for the fatigue behavior simulation in question. Especially since
I'm sorry for interrupting. We see always the introduction slide. I'm not sure that it is correct. Okay.
Okay. I was just done. Okay, no problem. So here you can see a bit of the information about this new composite, which is gaining a lot of importance recently due to some very favorable properties. Here you can also see in short how it is manufactured, and you can see the honeycomb structure, which is particularly interesting since it is not so well researched up to this point in terms of its behavior under various loads. The characteristics of the paper here can be seen. Its main advantages: high mechanical integrity, good mechanical properties, insensitive to moisture, resistance to chemical and flame effects, and many other adverse effects. And of course, combined with its lightweight, this makes it ideal for aerospace structures. Now, of course, we have yet to determine how well it behaves under fatigue. So here, this is what I was telling about its orthotropic behavior and the formulas which at some point we will be using to simulate its fatigue behavior. And here you can also see those properties if anybody is interested, and how the honeycomb mesh actually looks. So here first we will show a quick overview of some of the previous simulations which were made in Nastran as opposed to the ones we're currently working on, which are going to be performed in ANSYS. This is a simulation of a 3-point bending with our typical results shown here. And here you can also see the actual experiment performed on one of the specimens. So as I said, we were using ANSYS version R19.2 for this. And so far we have made functional static models and are currently working on the fatigue one. There's just some problems that I need to sort out in the next few days before the model becomes fully functional. So like I said, first we worked with the aluminum, but once that is done, we will move on to Nomex as a more complex material. And then we will compare the results to see what the differences are. So we also, for the ANSYS simulation, we also made a 3-point bending, which with boundary conditions, which would correspond to the end loads, which would correspond to the real experiments to determine the critical locations with high stresses where we can expect the fatigue cracks to initiate. In our case, there were actually 2 locations with very similar values, so both of them will be considered. Here you can see the boundary conditions. The end of the model, both ends of the model were fixed for the purposes of this particular model, and the bar you can see in the center is used to transfer the loads. So we can get better results. Just a second. Here you can see some information about the models, how the contacts between the parts were defined, and they were all like two-dimensional, but we defined a thickness of 0.12 millimeters. This was something we had to change later, which I will explain. And here you can see the results for the 3-point bending. This is the strain deformation, which was as expected. And here we have the stress distribution. The highest values were in some small parts of the support, so we can disregard that. The ones that are interesting are the ones closer to where the load was acting, which you can see here, very close to the load bar actually. And also on the bottom, with these having very similar magnitudes, so both will be considered at a later stage. So we have gotten sufficiently realistic results in this case. The stress and strain here were low, but our goal wasn't to force the model into plasticity. It was just to get the idea of how the stress, about the stress distribution. And we have two locations that will be considered for. Okay, so already covered this. So now we are going to go into the model for 3-point bending that will have the fatigue crack in it, which I will show you soon, but now here you can see some of the changes. We cannot go with the 2D models with an assigned thickness. We had to change it so that it is fully 3D by assigning it, by actually changing the geometry and taking a smaller section of the model to make it simpler in these first iterations. Later we will probably try it with the full size of the specimen. The boundary conditions were also changed, and here you can see the model as it currently looks. You can clearly see that it is three-dimensional now, and you can also see where the fatigue crack is placed. This is one of the two critical locations. The boundary conditions this time will involve only the bottom edges being fixed to see if that will make any significant difference. So currently the initial crack length in the model is 0.5 millimeters, but that can be varied at any point. And of course, another model will be made with the crack at the center of the bottom plate below where the load is acting. So that's all I can tell you for now. I hope I'll have more time to deal with this in the future, and that I will be able to maybe get some new results in the next few days.
Okay,
so
thank you very much. Thank you very much for presentation, and of course for the time. I'd like to check our Q&A. Now I see that we don't have open questions, so I'd like to. Oh, yeah, I have just one question from Alessandro Zanarini. Are you using your model for dynamics also?
Am I using? Sorry.
Are you using your model for dynamics also? For dynamics?
Yes, it will be used for dynamics, for fatigue crack growth simulation using smart cracks in ANSYS.